I, as a science nerd and a burgeoning physics or a nascent physics nerd, have read some books on popular physics and interpretations and so forth. So there's a few theories that I wanted to throw at you in a quick popcorn style and just get your quick take on them. Okay? All right. So Einstein, in a 1955 letter of condolence to the family of his lifelong friend Michael Besso, wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion." Quick take.
So something that does seem to be fundamental is causality. While time itself is something that can be manipulated and twisted around, it does seem like, yes, the past does influence the future and not the other way around. But indeed, when you look at the equations of fundamental physics, time is this malleable thing. And while causality seems to be preserved, exactly the notion of time orderings is something that is indeed flexible, as Einstein said.
Donald Hoffman, professor of cognitive science at UC Irvine, he wrote a book that I read a few years ago. He talks about the essentially interface theory of perception, this idea that through evolution, we essentially solve not for being able to see the world well, but being able to survive. And so ultimately he talks about reality being this interface. And he says famously, space-time is doomed. It's not real. It's an interface that we impose on reality. Thoughts on that?
Yeah, so quantum field theory, the mathematical framework that I work on, really takes space-time as the tapestry on which everything happens. But we know that eventually, if you get enough or extreme enough gravity, that indeed the structures of quantum field theory start to break down. And while there is a notion of quantum gravity that works for a while, you can talk about gravity in terms of gravitons for a little while, eventually you get a black hole, or eventually you get the Big Bang, start of the universe, and the notion of space-time completely collapses. And so indeed, the fundamental description of the universe will probably have space-time as being an emergent property. But for the work that I'm doing at the LHC, space-time is the tapestry on which everything else is painted.
Awesome. So in popular fiction, and it's almost become sort of slang, talking about I'm glad that I'm in, or I'm not glad that I'm in this what's it called, like branch of the universe, or this reality, right? It's become a meme in a lot of cartoons. When I dig into that, there's essentially a lot of it has to do with quantum mechanics. There's a Copenhagen interpretation of quantum mechanics, which states that, upon measurement of an observer, a wave function collapses into a single definite state. I think Hugh Everett's theory of the universal wave function says that each branch of this superposition is equally real, and we exist within each of them. Your take, Jesse.
So maybe just to say where this is coming from, the challenging thing about quantum systems is that you also have to take into account the quantumness of the observer. And you can't separate you yourself as an observer from the quantum system that you're trying to study. And this makes it really complicated to describe. One way of describing it is with the collapse of the wave function. The other way of describing it is with the many worlds interpretation. Mathematically, you get the same answer. But I would say that philosophically, what I like about the many worlds perspective is that it preserves the notion of probability. And I'm not sure that I would say that each branch of the universe has the same notion of reality, but it has certainly a notion of probability in the same way that if your favorite sports team loses, there was a branch of probability in which they won the game. There was some betting odds that they won. Yes, that's maybe not the universe that you're occupying, but it's not as if the fact that you observed the system to be in one state doesn't mean that there wasn't a reality or the possibility that your team might win. And similarly, the fact that you've observed something doesn't change the fact that there really was a quantum probability for you to have seen something else. And in that sense, I like the Everett type of approach to things, because it preserves that notion of probability, and probability seems to be kind of fundamental to the description of the universe.
Okay. So if your favorite sports team did lose, you can't necessarily take solace in the fact that they are winning in a different universe. They might just have lost.
They might just have lost, and yet you might have been perfectly justified in placing your money on that team. Yes.
Yeah. Great. Last one, which relates to our conversation in AI. Demis Hassabis, the founder of DeepMind, on his Twitter, I believe since last time I checked, He says, seeking to understand the fundamental nature of reality or of the universe. And he's also said, if we solve intelligence, then we can use that intelligence to solve everything else. And by everything else, he means a lot of deep scientific questions. Clearly, he's been all in on this. But yeah, your perspective on that.
Yeah. So first of all, it's an incredible idea that if you could take aspects of human intelligence and really scale it up with computers, you think about what human minds have been able to do over the centuries and really have that kind of amazing growth if we can scale it up. I think my perspective is one, the challenges that we're facing are probably ones where intelligence alone is not going to be enough, or at least human intelligence style alone will not be enough. And actually, one of the things that computers are able to do is allow us to transcend beyond human intelligence and even come up with new types of intelligence, or at least new ways of processing or parsing data. So while it's very seductive to think that, all I need to do is build an intelligent system in the human style of intelligence and unleash it, actually, my sense is that we're going to see that there's multiple different types of intelligence good for different types of problems. And there are probably still problems for which brute force search with the computer algorithm, that might be the best path forward, and that the kind of human intuition may not actually be relevant for all scientific problems. And so more generally, I'm enthusiastic about computing mathematics statistics as an engine that drives things, of which intelligence apparently seems to be subsumed under that umbrella, remarkably to me, under the banner of AI. But it may be that even more traditional computational strategies will be equally important, and we should not seek intelligence by itself without also pushing on the frontiers of computing more generally.